Start from current slide. And before we get going today, I'll turn on the light and go over a few announcements. A few of these you've heard before, and then toward the end there'll be some you probably haven't heard, but probably are at least somewhat aware of. So let me first hit these. First Call Quality Services is a company out of Indianapolis, Indiana. That's about all I know about it. They are currently over here at the One Stop Career Center in the Millsap building. That's the building just on that side of the loop that goes around this building. Just outside that loop, just about dead across from us, is the Millsap building. They're taking applications for a job fair. They're looking for quality inspectors at $11 an hour, team leaders at $13.50 an hour, and they're looking today, Tuesday, March the 6th, next door at the One Stop Career Center in the Millsap building, from 9, which they started just a little bit earlier this morning, until 1 o'clock this afternoon. Now that's for us, any of you students who are interested, but also for anyone out in the community as well. So if you know someone who's interested in a job such as this, get on the horn to them and tell them to get there before 1 o'clock. Benefits are available. In addition to pretty good pay, benefits are available. Applicants must have a clear background check, a driver's license, high school diploma or GED, and automotive manufacturing experience is preferred but not necessarily required. And if you want more information, there's not a lot of time, but Ms. Brenda Thomas and Ms. Dorothy Henry over in the One Stop Center in the Millsap building. And here's Sarah. All right. Next, Ms. Nyla Gerasi is always looking for students to be participating in the math team. They're having practices already. They won't have a competition until next spring, but they want to get you into the mode and thinking and getting ready for the competitions. They meet every Friday at noon and every Monday at 3 on the Birmingham West Campus in the Science Building, which is the C Hall, and that is in room C100. Okay, I blank on what the last part of it. It's a lot of fun, and you really pick up a lot of good skills in math that helps you in your future courses in math. So if you're at all interested, then consider participating with them. We have tutoring that is going on both campuses in several locations. On this campus, Student Support Services up here on this floor, and then the floor below us, the Space Center, and then on the Birmingham campus they have STEM Lab. They have some Student Support Services, and they also have the Space Center there as well. So there's lots of opportunity for tutoring on both campuses. And I don't think any of you are graduating, right? But if you know of someone who is, there was a meeting last evening on the Birmingham West Campus. There's a meeting this afternoon at 1:30 over here in Ethel Hall building. And then there's a meeting tomorrow at 1:30 the Birmingham West Campus at the ACAP building, first floor theater. Okay. Now, those are the formal ones. Here are the ones that come from my schedule and how that may affect you. This, by the way, I don't know if you noticed last night, with all the thunder and everything else, it was midterm, sometime around midnight last night, okay? That was midterm, okay? The last day of the first mini-term was yesterday. The first day of second mini-term is today. Okay, so what does that mean? It means several things, okay? And let's first keep it close to home. I, unfortunately, pick up 2 second mini-term classes, okay? None of my 4 classes now were first mini-term. They were full-term classes. So I went from 4 classes a term to 6 classes for the second mini-term. And since those are twice is long because there are many terms. It's like having 8 classes, It really makes it pretty tough. Okay, so anyway, my office hours changed drastically. So let me start with Tuesday, Thursday. Before today, my Tuesday, Thursday office hours started when this class gets out at 10:45 until 5:15 in the afternoon. Oh, that was so nice. Plenty of time to work on stuff. Yep, really good. Okay? Today, and from now on Tuesday, Thursday, the office hours are from 10:45 until 1:15. Because at 1:15, I have a physical science class here in this room, or what room is in, but that's where the class meets. That goes, because it's a mini-term class, it starts at 1:15. Now, the reason it starts at a weird time is a lot of mechanics who are on, that's why we offer on mini-term. They do co-op programs. They work half a term and they're at school half a term. Well, the second-year students are back in school starting today, and those that are taking this class, they get out of their automotive classes at 1, and then I give them 15 minutes to grab a bite or whatever and get over here. So at 1:15 we will start today. Because it's a mini-term course, 3-hour course, that means we meet 2.5 hours a day for class. So from 1:15 to 3:45. But because it's a science class, we also have lab. So we have 2 hours of lab. So from 3:45 to 5:45, we're in lab. Now, we're not technically break it down that strict, but we're in class from 1:15 to 5:45. So, and then as soon as that's over with, I gather my stuff and I leave campus usually by 6 o'clock. So there went office hours. I mean, still got some, but it's much shorter on Tuesday and Thursday. On Monday and Wednesday, the nursing or the allied health, or whatever program they call it, the health professions, are adding a brand new program called sonography, which is sonograms and things like that. And part of that program requires a physics course. And since my usual physics instructor is maxed out in the number of hours he can do, I get to pick up the second mini-term physics course. And it meets Mondays and Wednesdays from 4 to 6 on the Birmingham East Campus. Well, Mondays and Wednesdays I have a class that goes from 2 to 3:15. So as soon as that class is over with, I got to get up all my stuff together and head over to the Birmingham East Campus and then be ready to teach a class at 4 o'clock. So I only have maybe about 15 minutes in there to get everything together and out. So it's not really a lot of time for advising or anything else. So basically my office hours on Mondays and Wednesdays are now 7:45 to 9:30 as they were before, 11:15 until 2 o'clock, like it was before. But before I had 3:15 to 5:15 gone. Those are not there anymore. Okay. So I still have office hours all 4 days. Now, one other, this has nothing to do with mini-term, I have another treatment coming up on Friday, so I will not be on the Birmingham campus Friday, or this campus either, at all. Because treatment basically lasts all day long. They've gotten me out a little earlier some days, but I'm in no shape to come back to campus. I mean, I'm tired and sort of worn out, so I drive home and go to bed usually. So no office hours this Friday either. All right, any questions? Okay, I was hoping others would come in. They aren't here yet. Where we left off last time was on Chapter 4, Trigonometry, 4.8, Applications and Models, and we're at the top of page 330, Trigonometry and Bearings. Now, there's not a lot of difference here except how we orient things, okay? So, that's what sort of is almost the only big difference going on here. In surveying and in navigation, directions can be given in terms of bearings, okay? And actually in navigation, I was in the Navy, there's all sorts of different bearings. There's true bearings, there's relative bearings, there's bearings that roll around in a wheel. That's a different country, okay? What a bearing does is measures the acute angle that a path or a line of sight makes with some fixed north-south line. Now that's a true bearing if it's with the north-south line. So let's say I'm standing here facing north. That's approximately north anyway. Okay? Now, I can measure an acute angle if I'm facing north here, anywhere up to there. Now that would be east of north, right? Anywhere this way would be west of north, okay? North is just about here, approximately. So south would be here. So if I'm facing south, I could do any acute angle from here to there. It would be east of south, and any acute angle from here to there would be west of south. I've got the whole horizon covered then, all with acute angles that are measured from either true north or true south. Okay? So here's how we write those bearings. This is an example. South, 35 degrees east. Now what would that mean? South says face south, okay? And then do 35 degrees east of south, that's where it is. That would be the object that I'm looking at, the direction I want to take, or whatever it is, that would be what that is, okay? That's 35 degrees east of south. Face south, 35 degrees east. Now you see, that's where a little bit of difference came before. Before, we always measured everything relative to the positive x-axis. No longer. Now we're going from positive y or negative y. We're measuring our angles from there. Okay? You tell me what that name would be. Say again? Okay, that's how we would typically say it. How we write it is north 80 degrees west. Always give what direction you're facing first, and then how many degrees east or west it is. So you always give north or south first, and then how many degrees west or east from north or south. What would that be? North 45 degrees east. Perfect. Okay? So that's how we name our bearings. Here's how we use them in a problem. Okay? This is example 5. A ship leaves port at noon. Port is over here at position A. Okay? And heads due west. Must be a west coast ship. Okay? Sydney's here. All right. We're on page 330, example 5, trigonometry and bearings. So a ship leaves port at noon and heads due west at 20 knots. Now, does anyone know what a knot is? It's not a tangle in a string or something. What is a knot? Okay. A couple of things difference here. It's how many nautical miles per hour. Was a nautical mile different from a statute mile? Yeah. Okay. A statute mile, does anyone happen to know how far a mile is? In either feet or yards? Huh?
In terms of what?
I'm sorry.
In terms of what?
Feet or yards? 5,280 feet. Perfect. Or 1,760 yards. Exactly. Okay? What a nautical mile is 2,000 yards. So it's a little bit longer than a statute mile. A statute mile is 1,760 yards. A nautical mile is 2,000 yards. That would be 6,000 feet rather than 5,280 feet. What's that?
I said that's a lot easier to remember. I can get to do that.
Yeah, it is a nice round number. Yeah. Okay. So, and then a knot is how many nautical miles per hour. So if you're going 20 knots, it's a little bit more than 20 miles per hour on land. It would be maybe 21, 23, something like that. A little bit further, not a lot further. Okay. So he leaves port at noon, or she, a ship is fitting. Okay, she leaves port at noon, and it's due west at 20 knots. Okay? at 2 p.m. Now, what does that tell you? How long has it been going? Left at noon, 2 hours. And if it was going 20 knots, which is 20 nautical miles an hour, how far has it gone? Okay, 40 nautical miles. So we know that during due west, okay, it was heading out to sea, due west, for 40 miles in 2 hours. Okay, but at 2 p.m. the ship changes course to north 54 west. So north 54 west, you stop and look due north, and then go 54 degrees to the west of due north. That would be that way. Okay? So that's where we're heading now. Okay? Find the ship's bearing and distance from the point of departure at 3 p.m. So how far did they go at this new bearing? 1 hour. And how far would that take? 20 nautical miles. Because you didn't change speed, all you changed was your direction. Okay? So this triangle represents what you did. Leaving port, due west, 2 hours, 20 knots. That would be 40 nautical miles here. Change your bearing to 54, north 54 west, and you go up this way for another hour. That's another 20 nautical miles, and that's where you are. Now the question is, find the ship's bearing and distance from the point. So the bearing is going to be from due north, because it's north, this many degrees. Okay? And we don't know how many that is. That's the first thing we're going to, but that's one thing we're going to try to determine. The other thing we're going to determine is how far you are from port as the seagull flies. I mean, as the crow flies. Yeah, a straight line from A to, and they named this D. All right. Now, they made up a few things. They said port was at point A. Your turn was at point B. You wound up at D, and what they had here, this imaginary point right here, you were never there, but they named that C because that's where your right angle is. And we're doing right angle trick, right? All right. Now, which of those questions is going to be the easier to find, or the first to find, the bearing or the distance? What would you think? Yeah, I think the distance will be better because you got to get the distances before you can calculate your bearing. Okay. So, how are we going to determine the distance? Okay. Well, let's break it into pieces. You know how far you were 2 hours in. Okay? You're right here at point B. That's 40 nautical miles from A, due west. Okay? Then you changed course and went up this way. So if you can find the distance that you moved horizontally, westward, and northward, so that's what angle, the length here they did little d and little b, then add AB to little d, and you got the, you might say the horizontal component of your distance and your vertical component. You really don't do that either. Okay? And then from there you can calculate C. Right? Okay, a lot of arm waving and suggestion. Okay. So, how do we determine? What's the first thing you want to get? You choose. Second? Little d. I like the idea because that gives you, add that to the 40 and you're going to have your horizontal component in this direction. So how do we get little d? What do we know? Okay, we know this angle and the hypotenuse. We're looking for this side. Is this angle really going to tell us what we need? Yes. From what? 90. You want the complement of that angle. Okay? So there's our first step, is finding the complement of B. And what would that be? 36 degrees. Perfect. Subtract 54 from 90 and you get 36 degrees. Okay? Now how do you get D from that? Again, you know the hypotenuse and the angle. You want D. And in that little triangle here, what's the relationship between D, the hypotenuse, and the angle? It's what? Adjacent over hypotenuse is what operation? Cosine. So we know this, that cosine of 36 degrees is equal to adjacent, which is D, over hypotenuse, which is 20. Okay? How do we get D? How do we get D? Multiply both sides of the equation by 20 nautical miles. Okay? These 20s go out, and D then becomes a little louder. 16.18. Okay. Now, since they're only giving nautical miles, knots, you know, I'm not even sure we got more than one significant digit. Let's just leave it to 16. That's going to be approximately 16 nautical miles. Okay? So that added to a 40 makes the horizontal leg of that to be what? 56 nautical miles is the horizontal component of where he ends up. Okay? What you want to do, go for next? B. Okay, little b. How do we get that? Say that again. You can either use Pythagorean theorem or you can use the sine of 36, right? Which would you prefer? Sine? Okay. Let's do, what is your B then? Well, let's write down the relationship. Sine of 36 degrees is equal to B over 20. Okay? That's nautical miles. Again, multiply both sides by your 20 nautical miles. And the 20s go out. And what does B wind up being? Okay, let's round that to 12. Okay? Okay. Now, notice I did rounding there. If I were going to use Pythagorean theorem, I would, even though I might write this down as 16 nautical miles, I would leave everything on my computer screen there and do that squared plus b squared is equal to 400, which is 20 squared, subtract and stuff, and then take a square root, and hopefully you're going to get very close to the same answer. Do not use your rounded number, even though you don't have that many significant digits, in further calculations. Use as many digits you can grab hold of for the calculations. But given the answer, you round it. Okay? Now, what we have is the horizontal component of this big triangle here is 56 nautical miles, and the vertical component is 12 nautical miles. Now, again, if you have those on your screen, if you still have those down, leave that 11.75, whatever it was that you had there, square that, because that's the only thing you can do with this one. If you still knew what that first one was, it was 16 point something another. If you, that plus 40, you know, whatever that is, square that, and then add those two squares together, and take the square root of the sum. And what do you get? And if you didn't keep all those things on your screen, you're still going to be okay. What would your C be then? Anyone done it? I was still working on it. A little louder. 57.39. 39?
39.
Huh?
39.
39? Is that what you said? So I'm going to leave that at 57 nautical miles. Okay? I'm probably not going to be at the same answer as the book because they always throw in decimals that they can't justify. But there's that. Okay. So we've answered the second question. What's the distance from port? About 57 nautical miles. Okay? Now, is that how far he traveled? No. They did 40 plus 20 was 60 nautical miles. So you know the distance from port, it better be less than 60 because you can't get a straight line being greater than, 2 legs. So yeah, that making sense so far. But how do you get the bearing? How do you get the bearing? Okay, first, show me what arc to indicate on our graphic there what the bearing is. It's from what to what? Okay, the bearing is going to have 2 letters and a number, right? Okay. We don't know the number, that's what we're looking for. What letters would we be using? North and west. So it's going to be north so many degrees west. That's going to be the bearing. What would indicate those degrees? Not the value of them, but just what would be your arc that would show that? You go from north toward west until you hit the path. That is going to be my bearing. Okay? Now, what are our calculations going to give us? Based on what we've calculated so far, what angle can they give us? They give us angle A here. Okay? Right? Now, angle A, how is it related to the angle we're really looking for? Yeah, complementary angle to it, exactly. So if we can calculate angle A, then we take the complement of that, which is subtracting it from 90, and that gives us a bearing we're looking for. So that's our procedure. How are we going to get there? And frankly, there are at least 2 different ways. Probably 3 different ways to get there, based on what we know already. Well, let's consider what we know. We know the distance from A to C, don't we? It's approximately 57 miles. Okay. We also know the distance from C to D. That's approximately 12 miles. 12.75 or something like that. We also know the distance, C. That's about 57 nautical miles. So what can we use? Frankly, we only need 2 of those 3 pieces, depending on which 2 you want to use. How can we go about getting not the angle that we need, but the angle A? Think about angle A and knowing any one of 2 sides. Say again? Yes, which trig function? Okay, if you use sine, what would you use? Sine of angle A, I'll write it down. Sine of A would be equal to what? A little while? Okay, 12 divided by 57. Okay, you can punch that in the calculator. What is 12 divided by 57? Keep all the digits you can. Just a simple division, 12 divided by 57. Blah, 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 okay? Now, with that in your calculator, how do you get what angle A is? Second? Yes, exactly, the arc sign or the inverse sign. So with that in the calculator, just hit your inverse sine key, and you should get A. And A would be approximately what? A little louder? 12.15 degrees, I hope. Okay. I'm going to round that to 12. Okay, and then the bearing, what we're really looking for is what? Say again, 78? Exactly. So our bearing would be north 78 degrees west. That's where the boat would be, the ship would be from the point of north 78 degrees west at a distance of about 57 nautical miles. Make sense? Definitely easier to do the distances first and then come up with the other. Now, again, we had lots of rounding going on there. It's best to try to minimize your, only use rounding for the answers you're given. Minimize the rounding while you're doing your calculations. Okay? So let's see, with all that rounding that we had going, what we get. First thing they did, figure out what angle B is, and that was 36 degrees. We did that. Excuse me. Two sides of that triangle can be determined by B is equal to 20 times sine of 36. We, I think, did it a little more reasonably than that, but that's what we came up with, and D was 20 times the cosine of 36. And then they used the tangent. And like I said, back here, you could use any one of the three angles. Y'all chose to use sine, and the sine was B over C. The cosine would have been the 56 over 57, and the tangent would have been B over 56. So any one of them. Okay? And the tangent would be B over D plus 40. That would be, and they, by doing it this way, they don't stop and round anywhere. 20 times the sine of 36, that's going to give you big, long, hairy decimal number, divided by open parentheses 20 times cosine of 36 plus 40, close parentheses. That gives you a big, long, hairy decimal number. Divide that out, and you get the tangent of A, which would then be 0.209249, and then you do the inverse tangent of that, and you get 0.206273 radians. Why are they in radian mode? I don't know, because the angles that you were given was in degree mode. You convert that to degrees, and that's about 11.82, and what did we say? 12. So we were not far off in spite of all of our rounding. Okay? So they actually went about finding the angle first, and now you're going to go back and find the, and then that's the angle A. Subtract that from 90, and you get 78 degrees, which is exactly what we got. rounded to 78 degrees, and the bearing is north 78 degrees west. I do not feel like you can get more precision out of the problem than you put into it. Since the only angle they gave you was 54 degrees with no 2 decimal places after it, how can they get 2 decimal places out of the answer? I think the best you can say is 78, okay, which is what we did. Okay? And then finally, which we did first, from the triangle ABC, we have the sine of A is B over C, which we have already, well, here is where I really feel like this is an awkward way to do it. Because notice what they're using to get sine of A will be B over C. B, which we already calculated. C, we haven't calculated, so C is going to be B over sine A. Well, sine A was a calculation, B was a calculation, so you already got inherent in this, unless you keep all the digits that you had, round-off error. So I think doing it the way we did minimized this, because they've already done the calculations back when they were doing this. The 20 sine 36, 20 cosine 36, add to 40. You've already done all that, so why go back and use what your calculations based on those were? Just use the numbers that were given, you know. But this works too. 20 sine 36, which we already did was B, divided by this calculated angle we had, 11.82. You already had another way to do it, and we did it. But still came out with about 57 nautical miles. And what do we have? 57 nautical miles, okay? So, whereas they did the angles first, almost calculating the distances they needed, and then they went back and calculated the distance based on the angle they just calculated, rather than from as much original data as they could. And we came out with the same amount. The distance from port was about 57 nautical miles. Oh my goodness. I'm so running out of energy. Sorry about that. Well, guess what? There's a checkpoint there. So I would definitely want to do those as soon as you could. Once you get out of class here and don't have any other classes, do that checkpoint and then check your answer at audio video solution at larsonprecalculus.com, and you can see and hear how they suggest you do it. Okay. Man, I feel like I just want to go to bed. So, let's move on to harmonic motion, another application of trigonometry. Okay. The periodic nature of trigonometric functions is useful for describing the motion of a point on an object that either vibrates, oscillates, rotates, or is moved by wave motion. And that covers just about everything we do in real life. You know, objects are either vibrating, oscillating, rotating, or moving in a wave. Okay? And all those are defined by harmonic motion. We already talked about, we did an example back in the first half of this chapter of your tides. And we saw those were very much related to harmonic motion, sines and cosines. Okay? So, here we're going to deal with a spring. Now, this is a vertical spring. You could do a horizontal spring just the same as well. But if you have this mass, whatever it happens to be, at the bottom of the spring, hanging there in equilibrium, not moving up or down, just hanging there. That's what we call its equilibrium position, right there. Now, there's a couple things you can do to this. What they suggest that you do first is you take hold of this and stretch it, maybe not as far as you can, but a certain distance down there before you spring to spring, before you distort it so much you can't pull back, and we'll call that its maximum displacement. And they're saying stretch it 10 centimeters. Now, if you're holding that mass down there at 10 centimeters, you're having to exert a force because you're stretching the spring is pulling back up at you, right? Now, if you were to release it from here, where's the spring going to go? Back toward its equilibrium position. Always moves toward its equilibrium position. Not always, not quite. But what happens? When you release it, what's the speed of that spring, of the object? Right when you release it? 0. Because you've been holding it there at 0, and the spring starts pulling it back, so it starts increasing speed going back to the equilibrium position because the spring is exerting a force on that. And the force, and we're going to do this in just a minute, is related to what they call the spring constant. Okay? It's spring constant times the amount of displacement. Okay? So as it is pulling up here, the force is the greatest, and the speed starts at 0 and starts increasing because the force is pulling it up. And right about the time it gets to equilibrium position, the force is now going to 0 because it's 0 here. Okay? But the speed is at its maximum. So it's going to overshoot that. And it's going to go up here to about 10 centimeters above that before now it's compressed the spring. Now the spring is pushing back this way, slowing down the motion as it goes up here. So the motion speeding up as it goes here, reaches a 0 speed here, maximum speed here, 0 force here, maximum speed here. Starts slowing down here until it reaches 0 here. And then the spring is going to push it back down, and it goes like this. And that's called simple harmonic motion. And if you ran a strip chart recorder past that, and you had a pen here, you would be making the sine of a cosine. Right? Simple harmonic motion. So that's where we use trigonometry here. Now, let's think back. What were some of the names we had for our parameters in simple harmonic, in trig functions? A sine B x plus C plus D, those kind of things. What was our A related to? Amplitude. What would be your amplitude here? How far you stretch? 10 centimeters. The B would be related to let's just for now say to that spring constant. We're not going to get into details about that. C, since we have it starting here, if we started it from down here, actually the A would be a minus 10. The amplitude would still be 10, but the A would be minus 10 when we started from there. I would use a cosine function then because we're starting from a negative max. You can use sine and just have the phase shift. So since you're starting from a negative mass, your C would then be 90-degree phase shift. Normally it would be at minus 10. And D, if you start at equilibrium at 0, you have no displacement there. Okay. Suppose the 7 centimeters is the maximum distance the ball, they call it a ball, I call it a mass, moves vertically upward or downward from the equilibrium or at rest position. Suppose further that the time it takes for the ball to move from its maximum displacement above 0 to its maximum displacement below 0 and back again, one complete cycle is 4 seconds. Okay? Assuming the ideal conditions of a perfect elasticity and no friction or air resistance. Not likely to happen, but if you could assume that, the ball would continue to move up and down, the weight faster go up and down, uniform and regular manner forever. There's always going to be some friction inside the metal of the spring, okay? And there's also always going to be a little bit of air resistance. Unless you happen to be on the moon or somewhere in outer space, you know, which most of the time we're not. Okay? Now, from that spring, you can conclude that the period, or the time for one complete cycle, would be 4 seconds. Right? That's the time it took from one max up to the other, back down again. Or up here to down, to back again. One complete cycle is 4 seconds. So we know the period. And since we're using either a sine or a cosine function, we can now come up with the t. Right? So that's all we need there. The amplitude, which is the absolute value of that maximum displacement, 10 seconds. Whether it's minus 10 or plus 10, the absolute value is 10. The frequency is the number of cycles per second. And if you notice, the period was the number of seconds for one cycle. So these are going to be reciprocals of each other. If that's 4 seconds, this is 4 cycles per second. A quarter of a cycle per second. Because it's going to go a quarter of it. If that takes 4 seconds to go from here to there and back here again, that took 1 second, 2 seconds, 3 seconds, 4 seconds. So it was a quarter of a cycle every second. So it's just reciprocal. Motions of this nature can be described by a sine or a cosine function called simple harmonic motion. And so many things in nature. Tides, daylight hours, lunar cycles, just about everything can be explained with simple harmonic motion. So here's the definition. Goodness, I'm not going to make it to 45 tonight. I don't know. A point that my wife is pretty mad I'm picking up these second miniature courses, but the only instructor that's credentialed to do it is already maxed out. Point that moves in a coordinate line in simple harmonic motion. The coordinate line here was vertical. That could have been horizontal. When its distance d from the origin at time t is given either by d is equal to a sine omega t. We haven't run into that omega before, have we? Did y'all realize that was an omega? You may be used to thinking of omega as being this thing that sort of looks like a horseshoe, right? Okay, that's capital omega. The lowercase omega looks kind of like a W. It's not, it doesn't have any ends on it, but that's lowercase omega. Okay? Or d is equal to a cosine omega t. Now this d is not your parameter d that we used before. This is just distance from the equilibrium, which is 0. Okay? A is related to the amplitude. Okay, and that's the value of A is the amplitude. And now your omega is just like our B was before. Before we did A sine BT, or BX, or something like that, your omega is just like the B. So, where A and omega are real numbers, it's just we usually use omega dealing with, we don't give it a name like, well, in fact, we did already. Remember, we did do this. Angular velocity. Remember, we did some examples like that. Tips of the wheel. Yeah, that we did do it. Okay. And omega now is like the B that we were using earlier in 4.5. The motion has amplitude of absolute value of A, just like before, and the period is 2 pi over omega. And the frequency, since we know is exactly the reciprocal of the period, is omega over 2 pi. That's a new one on us. You have so just a little bit of more nomenclature. Since frequency is directly related to omega, we sometimes call this the angular. We call it angular velocity, which it is, but you could also call it the angular frequency. Omega divided by 2 pi. Oh man, okay. So here's example 6. Looks a lot like we just had up here, but now we have it in fact, In the book, they don't draw it again. They use the figure they had before. But the example 6 is on page 332, but the figure is back on page 331. So to look at it in the book, you have to flip back and forth. Here they got it all down here. Write an equation for the simple harmonic motion of the ball described in figure 4.6, where the period is 4 seconds. What is the frequency of that harmonic motion? Okay, so they first are asking for an equation, and then they're asking for the frequency. Okay, actually, it would be far easier to answer the second question first, but we'll answer it forward. Now, when I was describing this before, I said, well, let's pull it down here and stretch it to 10 centimeters below equilibrium, like the -10. We didn't have to do that. We had another option. From the equilibrium position here, we could have thumped it real hard, okay, and given it an initial velocity here, that it went down just that far, stopped there, and then started going back and forth like that. So you can start at equilibrium with a thump, because it's not going to move anywhere without a thump, or you can stretch it down here and release it from rest. So it depends on where you want to start from. That's kind of up to you. It's going to give you the same issue once they tell you the period is 4 seconds. Okay. So now they say write an equation for simple harmonic motion of that ball or mass described in this figure, where the period is 4 seconds. Sort of snuck that in there, but it's pretty important. Okay? How do you determine that equation? First, tell me which trig function you want to use. Cosine? Is that what you said? Okay, what would that be? Your d is your distance. That's going to be what we're looking for, is equal to a cosine omega t. Okay? We don't have any other phase shifts or anything else. Well, we actually probably do, but we'll take care of it. Okay? No, we really don't. If we take care of it well. Okay, first, what's your A? Okay. Where are you starting from? Are you starting from this one? Is that your initial position? From there? Is that your initial position? You got to decide where you're going to start from. If you started from here and use a cosine, then this is starting at 0. You're going to have a phase shift in there. So you have to have some sort of phase shift there. If you're starting from here, you can use cosine with no phase shift, only here your A is -10. If you're starting from there, then your A is 10. Okay? So the amplitude is 10 because it's absolute value, but depending on where you're starting from, you're either going to start with 10 there or -10 here. So the -10 here then you don't have to have a phase shift in there. Pi, okay. If you start from here and use cosine, you have to have a phase shift of pi halves, because this is where cosine is pi halves. So, which are you going to use? The minus or the plus? Minus. Okay, let's start from there. So this will be, because you see A can be plus or minus the absolute value of A, the amplitude cannot be. So -10 centimeters. We're going to write it for now. Maybe later we won't. Cosine. Now, oh boy, how do we determine omega? What helps us determine that? What is omega related to? What do we used to call omega before this section? That's related to the period. They told us the period. So how is omega related to the period? Okay, say it again. Okay, the period is equal to 2 pi over omega. So therefore, omega would be what? Two pi over period, right? Multiply both sides by omega, divide both sides by period. Yeah. You just swap positions. Okay? And what was our period? 4 seconds. So omega is equal to 2 pi over 4, which would be pi halves, and that would be per second. Okay? Yeah. Or actually, cycles per second. That would probably be the better way to go. Or just per second. All right. Now, so here's our equation. Pi halves cosine pi halves t. That's it. Minus 10 cosine pi halves t. Determine the A from the maximum displacement. It's going to be 10. If you're starting from that down there, it'd be a minus 10. If you're starting up there, it'd be a plus 10. It doesn't matter. Sorry, over here you have to, I would use sine if I were going to use this one. Okay. It might be a minus sign because in the first place it goes down, that's the opposite direction. But whichever, okay? Your omega in your formula comes from your period, according to what you just did. That's going to be pi half. Because think of this. This is angle per second multiplied by t seconds, and that was just going to give you an angle. And you take those lengths of angles. Okay. And then multiply by your magnitude. Okay. Now, the next question, this final question, what is the frequency of that harmonic motion? Okay. Frequency is? Okay. Is that the frequency? Yeah, that's fine. Yeah. All right. So let's do it that way. Frequency is equal to omega over 2 pi. What did we say omega was? Pi halves over 2 pi. Well, the pi's will cancel out, and you have 1 over 2 times 1 over 2, which is 1 over 4. And that would be per second. Okay. Now, that's why I like to call omega the angular frequency and this the actual frequency. Okay? Because this is actually cycles per second. That's just per second. Now, if you go back just a little further, we see that frequency is reciprocal of the period. So since you knew the period, don't go through omega, just do 1 over 4. So yeah, that gives you the same thing. Okay. That's why when you said omega over 2 pi, so, oh yeah, that works too. But so much easier, 1 over the period. That is the frequency. Okay. Now, how bizarre. Amplitude was 10, whichever direction you have it going first, plus 10 or minus 10, the amplitude is 10. Period is 2 pi over omega is 4, which makes omega pi halves, which we got. But then they use the side function, sort of figuring you started from here and pinged it downward. Okay? And they really should have done a minus sign function if that's what they were doing. They did a plus. So that would be like if they pinged it up. Started at equilibrium, went up and down, up and down. So I think they were a little sloppy there. But it didn't matter which one you did. If you were starting here and did sine, then you would need to have a phase shift in there. So that's why we use cosine. Okay. Okay, and by the way, there's a checkpoint there too. Do it as soon as you can and use your audio video solution from larsonprecalculus.com. Okay. Oh, here's their, I forgot, I had the problem here. Because the spring is at equilibrium, D is equal to 0. When T is equal to 0, that's assuming you started there, D is equal to A sine omega T. That was their rationale for doing it. That means you had to ping it. You had to give it some initial velocity to get it to start moving. Otherwise, it just sits there. It's not going to do anything unless you either stretch it, which then has a new initial condition, or you ping it with initial velocity. Moreover, because the maximum displacement from 0 is 10, and the period is 4, we have amplitude, absolute value of A is 10. So A would be the plus 10 or minus 10. And the period is 2 pi over, the period is 4 seconds, they told you that. And that's 2 pi over omega, because omega is like your B was before, which is 2 pi over B, 2 pi over omega. And that makes omega equal to pi halves. Okay. So your equation of motion would be either plus or minus 10 times the sine or cosine of pi halves t. Notice that the choice of 10 or minus 10 is whether initially the ball moves up or moves down. Actually, their figure showed it moving down first, but that's why I would have used minus 10. The frequency, and they did the same, use omega over 2 pi, which is pi halves over 2 pi, which is 1/4 cycle per second. Okay. Goodness gracious. I think I can hang out 10 more minutes. I just need so badly to get some caffeine or sugar or something. But I can make it 10 more minutes. One illustration of the relationship between sine waves and harmonic motion is the wave motion that results when a stone or a fishing lure or whatever is dropped into a calm pool of water. The waves move outward in roughly the shape of a sine or cosine wave. If you picture the equilibrium about the middle of this, it goes up and down, up and down, up and down, up. Now, in reality, they're slightly damped. The peaks get smaller and smaller and smaller. Good. That's because of internal friction between water molecules. Okay? But right near the center, that looks about like a sine or a cosine wave. I would call this one a cosine wave because it looks like at the center is at maximum, and it goes down, up, down, up, down, up. So that would be a cosine wave. But whatever. As an example, suppose you're fishing and your fishing bobber, okay, also called the float, is attached so it does not move horizontally this way at all, but it's attached. All it does is go up and down. As the waves move outward from the dropped stone, your float, or your bobber as they call it, will move up and down in simple harmonic motion. Okay? I don't particularly find this illustration all that useful, but I do know what they're saying in it. It is good. If it was here and the stone hit, and it started moving. The wave was moving upwards, and at any point, say here, sometime that's a distance x away, here it would move up and down like this, and it would be moving up, down, up and down. So that's your motion of your bobber. No, I guess what they're saying is if this is where the stone goes in, here's where your bobber is, or your float. Then initially, when that first wave comes along, it pulls it down, and then a little bit later, it's not pulling as far down, not as far, then you're at equilibrium, then you slightly raise, slightly more, raise more, until it reaches the maximum, and then it goes through the same. So the bobber is just doing this up and down. This is distance, I think, from where the stone fell in. Like I said, it's not a particularly clear illustration in my mind. But, whoa, they lost example 7. So let's us do 7 as well as we can. Consider the equation for simple harmonic motion of D is equal to 6 times the cosine of 3/4 pi times t. Find A, the maximum displacement, B, the frequency, C, the value of D when t is equal to 4, D at time t equal 4, and the least positive value of t for which d is equal to 0. This will be D, smallest t for which d equals 0. Yeah. Okay? Now, all they give you is the equation. What's the maximum displacement? 6, okay? We don't know what units 6 are, but 6, okay? So A here would be, I'm actually going to call it A is equal to 6, amplitude. Okay. Okay, that's all we know. Okay, B, what's the frequency? What's frequency related to? Period. How is it related to the period? It's what? Reciprocal. So the frequency is equal to 1 over the period. Right? What's the period? Is 2 pi over your omega. Yeah, is that what you said? I can't hear. Okay. So this would be 2 pi over 3 pi over 4. This is your omega right here. This is your A right here. Okay? So let's see what we can do here. That the pi's will go out, and this will be 2 divided by 3/4, which is 2 times 4/3, which would be 8/3. That is going to be your period. So what does that make your frequency? 3/8, exactly, the reciprocal. Okay? Let's make sure they're getting it right too. Yes, and you call those per seconds. Frequency is in per second. Okay. Now there's another name for frequency. I can't remember if we hit it last time or not. A hertz, HZ. You could call that 3/8 HZ, hertz. That's cycles per second, or per seconds. Okay? Now, the third part, the C part, is what is D when T is equal to 4? Well, that's fairly simple to do, isn't it? This is the C part. You just plug it in, plug it in. 6 times the cosine of 3 pi over 4 times 4, right? And what does that give you? 4's go out, and that would be 6 times the cosine of 3 pi. And what is the cosine of 3 pi? Okay, I think of my good old unit circle. Okay, it's not a unit circle, it's a 6 circle. Okay, so it starts at 1, cosine starts at 1, goes to 0 at pi 8/4, 6 at, so it starts at 6, 0, and then negative 6, 0, that's at 1 pi, at 2 pi it's back at 6 again, and at 3 pi it's back at negative 6. So, yeah. So this will be negative 6. Okay? And then D. And the D will be the smallest t for which D is equal to 0. Well, let's just plug it in. Put D is equal to 0. Have 6 times the cosine of 3 pi over 4t is equal to 0. We set D equals 0. And then guess what? We can divide by 6, right? And 6 divided by 0 is still 0. I mean, 0 divided by 6 is still 0. So we have cosine. Okay. So what we have, I'm running out of breath. The cosine of 3 pi over 4t is equal to 0. Okay. Well, when is cosine equal to 0? At what time? The first time it would be equal to 0. Not time. The first argument here. When would that equal 0? Cosine starts at 1. Not pi. Pi is negative 1. Pi half. Oh, you said pi half? Yeah, pi half. That's exactly right. So it's when 3 pi over 4t is equal to pi over 2. Does that make sense? Okay. And here again, we can divide out the pi's, and this will give you, let's multiply both sides by 4/3. I like that rather than dividing. Okay. Here, everything goes out except t, so t is equal to here. 2 will go into 4 twice, so 2/3 of a second. That would be the time at which you got the smallest time that you would get your displacement equals 0. So it starts off somewhere else, and probably at +6, okay? And then 3/4 of a second, 2/3 of a second later, it's at 0, okay? Make sense? All right. I think they got them all according to that. So there is a checkpoint down there. You can check that out. Okay. Yuck, we don't have time for our vocabulary. So we'll start that next time, huh? We'll start with that next time. Now, I did not get the test run off. They're made out but not run off. Would you like me to go on and run off copies for you and then bring them up here, or pick them up on Thursday? Huh? Okay. It doesn't take me long to run them off. You want them? Okay. What's that? Okay, well, we will. We'll do it next time. Sorry. It's just that I didn't want to take, if y'all have classes to go to. Okay, there's test one. Test one. Test one. Ha, here's test two. Now, how many of you need graph paper? Okay, so let me also draw some few sheets of graph paper.
Oh, you're still through.
Yeah, just saw some in here. Where was it? Ha, here it is. Okay. Okay, you got 9 to graph. You tell me, on a piece of graph paper, how many can you do? If it's front and back. 1, 2, 3, 4? Or you want them more crowded than that? Huh? That would be good. So let me, one of them's going to have 3 on the page. So do, yeah. 1, 2, 3, 4, 5, 6, 7, 8. Got one more to do, 9. You can squeeze it in somewhere. Okay, so I'll make 2 pieces of graph paper, front and back. Yeah, for each of you. And I'll make like that.
I'm still looking forward to tomorrow because it's my first day being off, and then I said, I'm working. Mondays, I'm not excited about Fridays 3 to 7:30. But at least get it over. And we have Thursday off, so that's good. Probably just like mandatory support. But I mean, half the time our guys aren't even going to be playing because it's a tournament. So, I thought they were. Did they not make it? That's. Sure, I'm hosting the tournament then. I don't think our girls are moving.
Is that been recorded?
Yeah. What should we say to people that are going to listen to this?
I don't know.
Jill said also remember how your schedule, so you have to be here all the time you have class, like she knows. As long as they provide food. And what are we doing on March 10th? Like that tournament? What is that? Said I need all retreaters to help me March 10th because we are hosting the volleyball tournament at Boston. Be available all day. Like we're not playing. We're hosting it. That confused me. Hopefully we're done with that around 4 because usually it's just like all my free time. girls are? So, that's measurements here. Oh, girls team is play here. At 1.
So I keep you waiting. Do you want to grab it? Okay. Sorry, keep you waiting. Oh, I should have turned off this. I recorded everything you were saying about